guys, and welcome to Unit 4. In Unit 4, we're going to be studying quadratic models. Yay! So we're starting off with our launch in 4.1. It's called Introductions to Quadratic Functions. I will be referencing our book, Algebra with Models, student workbook by Marion, Anton, and Karen Santoro. This is page 117 in my workbook. It might be a little different in your workbook, depending on what edition you have, but it is called a square garden. So we're going to be thinking about how to build a garden today. So let's get started. Okay, so before we jump into quadratic functions, let's quickly review the two types of functions that we've talked about already, linear functions and exponential functions. Because as we explore quadratics, we're going to talk about what's similar and what's different about these functions compared with linear functions and exponential functions. So linear functions, we know we can describe using the equation y equals mx plus b, or f of x equals mx plus b if we're talking about a function. M is the constant that represents the slope or rate of change of our line. We know how to calculate it. It's the change in output over the change in input. B is also constant, which represents the y-intercept, or as we discovered, the initial value. It's basically our starting value. X is our independent variable or input, and y or f of x is our dependent variable or output. I also want to mention that a linear function can have only one x-intercept. The exception being if we have a horizontal line that is not the x-axis, okay? So we saw that linear functions have this thing called a slope. They have this initial value, which is the y-intercept, and they can have an x-intercept, but only one, all right? So now let's quickly review exponential functions. So as we discovered that we can write an exponential function using the equation y, or f of x, equals a times b to the x, where a cannot be 0 and b cannot be 1 and must be greater than 0. We learned that b is called the constant multiplier. So with linear functions, we had a slope, which was a rate of change. But with exponential functions, we had this thing called a constant multiplier, which we calculated, which basically took our output, our first output, and we multiplied by the constant multiplier to get to our next output. A was also a constant, and it was the y-intercept or initial value. So again, with exponential functions, just like with linear functions, we saw that this y-intercept, this initial value, was very, very important. X was, again, our independent variable or input, and y, or f of x, was, again, our dependent variable or output. But we saw that with exponential functions, we did not have an x-intercept. The x-axis was actually an asymptote, which means that while our exponential function could get really, 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 really close to it, it never actually touched it. So there was no x-intercept. So for linear functions, we could have one x-intercept. But for exponential functions, we had no x-intercepts. An interesting difference. So let's begin our study of quadratic functions. We're going to start on workbook page 117 for me. It might be different for you depending on the edition of your workbook, but it is called 4.1a, a square garden launch exploration. And this is the situation we're being asked to consider. We are planning a square-shaped garden and explore patterns as we compare side lengths and areas of different sized gardens. Consider, this picture is directly from your workbook. I took it right out. You guys, I always say before you jump into the questions, right, just take 60 seconds and think about what's happening. What is the situation asking us to do, right? What is even happening? Make a movie in your head. So basically, we're being asked to go out to our backyard, look at the amount of space we have, and figure out what would be the best length for each of our sides to make a square-shaped garden. We want our garden to be a square. What can our yard accommodate? How long can the sides of our garden be so that it will fit into our yard, okay? And so we're going to have to play around a little bit to see, if we make, let's say we're working with the units of feet. If we make our garden 1 foot on each side, are we going to be able to fit it in our what's the area? Are we going to be able to fit in our yard? What about if we make it 2 feet on each side? So that's what we're doing. We're playing around with the size of our garden, all right, and figuring out what our yard can accommodate. So let's get started with that. Let's see how that plays out. So let's look at this first little square all the way to the left. So in that instance, we are working with what we're going to say is 1 foot, a side length of 1 foot, right? We have 1 foot going across each side, okay? That's what we're working with here, okay? It's 1 foot by 1 foot. Remember, this is a square, so the dimensions are going to have to be equal, okay? So if we have 1 foot by 1 foot, a 1 foot by 1 foot garden, then the area would be 1 foot squared. And you guys can see that, right? There's one little square here, okay? All right, remember the area is the amount of space inside. All right, well, maybe we can accommodate a bigger garden than that. So let's say now that we are looking at a side length of 2 feet. So 1, 2 feet, okay. All right. Okay, well, if that's the case, then the area would be what? Well, 1, 2, 3, 4. Now we have 4 squares inside. Okay, so our area is 4 feet squared, all right? Well, maybe we can accommodate a garden even bigger than that. Let's say we now extended that side length to 3 feet, okay? And again, right, we're going 1, 2, 3 feet across. And again, this is a square, so down the side, it's going to have to also be 3 feet, okay? Well, then what's the area now? And if we count up those squares, right, we can see 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, now we're dealing with an area of 9 square feet. All right, and we're just going to keep going with this, with planning out these different size gardens. Okay, we'll extend it to 4 feet. So if the side length is 4 feet, then the area has to be 16 feet squared, right? We have 16 squares in there now. And let's extend it one more time. Let's say that the dimensions are 5 feet by 5 feet. Well, then our area would have to be 25 feet squared. Now we have 25 little squares in there, all right? So we're just considering how the length of the side is affecting the area of this garden, right? Every time we extend it out another foot along the sides of our dimensions, right? What's happening to our area? That's what we're looking at here. How big of a garden can we accommodate? How long can we go on each side, all right? So now I want you to take just a moment to stop and think. What is happening? Make a movie in your head. Make sure you understand what we're doing in this problem. And then do you notice a pattern? So hit pause, take a second and think about these questions before we move on. So the first question our workbook asks us is to identify the variables. And we should be pretty used to this by now, guys. When we jump into these situations, these problems, that is the most important thing, to identify your variables. That should always be your first step, even if you're not asked to do it right out of the gate. You should always stop and think, what is my input? What is my output? What is my independent variable? What is my dependent variable? Because you can't really go very far without knowing that. So I want you to take a minute to stop and think about what your input and your output are. What is your independent variable and your dependent variable? And remember, we're working with side length and area. So take a minute, pause, stop and think, and then we'll talk about it. So hopefully you guys at this point, we're able to deduce that your input here, your independent variable, is the side length. I gave that the smart label S, okay? And the units we're working with are feet. And then your dependent variable, your output, is going to be the area of the garden. I gave that the smart label A, and my units are now, I want you to notice, square feet. And that's because area is the measurement of the inside of our square, which means we're multiplying 2 dimensions together, the length times width, right? So I wanted you to see that written out in English and also denoted with an abbreviation of FT and that little exponent of 2 for feet squared, okay? You might see it in different ways, so I want you to be able to recognize it in different ways, all right? So we're basically plugging in different side lengths, right? 1 foot, 2 foot, and getting out an area, all right? Which is why our independent variable, our input, is side length, and our output is area, okay? So next we're asked to make a table of values. And again, this should feel pretty familiar. When we begin our studies of different functions, we've always identified our variables and then made a table, right? It's important to see what's happening. Are we noticing a pattern? And tables show us patterns, right? When we have a table of values, we can examine it for a pattern. So we're asked to make a table of values and then examine the table for a pattern. Is it linear, exponential, neither, or explain? So I am going to do this one slide at a time. I'm going to give a slide to see if it's linear. We're going to do a slide to see if it's exponential, and then we'll take it from there. So on this slide here, I want to know, is it linear? So here we're just looking for a linear relationship. Let's start there. So I'm asking you, does this have a constant rate of change, right? That's what we learned about linear functions. When we look at our input and our output, right? Is our output changing at a constant rate as our input increases at a constant rate? So let's check. Let's see. All right, we always start with our input. So here's my table. On the left, I have my input, which we said was side length, and we gave it the smart label S. And on the right, I have my output, which is the area of the garden. We gave it the smart label A. So for our function A of S, let's look at the left side, our input side length, how that's changing. We want to make sure it is indeed increasing at a constant rate. So to go from 1 foot to 2 foot, that is an increase of 1. To go from 2 to 3, that's an increase of 1. 3 to 4 is an increase of 1, and 4 to 5 is an increase of 1. So yes, my input is increasing by a constant of +1. That's great. Okay, now we can check our output to see if that is changing at some sort of constant rate. So my first output is 1, and my second is 4. So to go from 1 to 4, that's an addition of 3. So we can see I'm definitely increasing. Outputs are definitely increasing, but is it at a constant rate? Well, let's see. To go from 4 to 9, that's an increase of 5. So already, like, alarm bells are going off in my head. Ooh, this is not constant. To go from 9 to 16, oh, that's an increase of 7. And to go from 16 to 25, that's an increase of 9. So right away, guys, I know my output is not changing by a constant, which means the rate of change is not constant, and this is not linear. Okay, so it's not linear. Let's see if it's exponential. Okay, guys, so we know it's not linear. Now, let's look at our table of values and examine it for a pattern to see if it is exponential, which means I'm asking you, does this have a constant multiplier, right? We know that about exponential functions. We should be able to look at the table and find a constant multiplier. So I left the input filled in already. We know the input is increasing by a constant of +1. We're happy about that. Let's look at the output to see if we can find a constant multiplier. So to go from 1 to 4, what do I multiply by, you guys? I multiply by 4. All right, let's see if that holds. To go from 4 to 9, oh boy, now I'm multiplying by 2.25. And if you don't know how I got that, you guys, you can just divide 9 divided by 4, right? To find the constant multiplier, we divide the current output by the previous output. So 9 divided by 4 gave me 2.25, which means 4 times 2.25 gives me 9. Ugh, so I'm a little unhappy now because I'm seeing that my multiplier is not constant. Well, let's just see what's going to continue happening here. To go from 9 to 16, now I'm multiplying by 1.77. And to go from 16 to 25, I'm multiplying by 1.56. So the output is not changing by a constant multiplier. There is not a constant multiplier, which means, sadly, this function is not exponential. So this function is not linear. It's not exponential. What is happening? What is this? So we're really puzzled, you guys, right? We were happy that our input was increasing by a constant of +1, okay? But when we examined this table and looked at our output, we found that it was not changing by a constant or a constant multiplier. So it was neither linear nor exponential. So what is it? So what I want to do is I want to take us back to when we were examining this table to see if it was linear, okay? So we looked at our outputs. We said to go from 1 to 4, we added 3. To go from 4 to 9, we added 5. To go from 9 to 16, we added 7. And to go from 16 to 25, we added 9. And we looked at that and we said, okay, they're increasing, but not by a constant, okay? And we said, okay, this can't possibly be linear. But as it turns out, we're going to take this a step further. So when we calculated these differences over here, this +3, +5, +7, +9, those are actually, they have a name. They are called first order differences, okay? So the first time we calculated the difference in output, we found a +3 and then a +5 and a +7 and +9. Those are what we call the first order differences. Well, we can actually take that a step further. And if you look at these first order differences, you guys, Okay, we have 3, 5, 7, 9. That sounds a little bit familiar, right? There's a pattern there. 3, 5, 7, 9. They're odd numbers, okay? And so we're starting to maybe think, oh, wow, there's actually a difference. I mean, there's actually a pattern in these differences, okay? To go from 3 to 5, we're adding 2. To go from 5 to 7, we're adding 2. To go from 7 to 9, we're adding 2. We've stumbled upon this constant pattern, this constant change. But the change is now in the differences that we calculated. So we actually do have a pattern here. Only it's not with our first order differences, it's what we call our second order differences. And as it turns out, when you have a constant change in your second order differences, that is a quadratic function. Okay, that implies we are dealing with a quadratic function. So if you need to, take a moment, go back to that last slide, and just listen and think about it again. I just threw this whole brand new concept of second order differences, this whole idea of second order differences at you guys. And that's a lot. So if you need to, go back, listen to it one more time before you dive into this next slide, okay? But if you're ready, we're going to talk about what quadratic functions are. What are they? So as we saw in our previous slide, quadratic function tables are tables of values characterized by constant second order differences of the output when the input increases by a constant. And we assume that those first order differences, we just assume that they are non-constant, okay? Which basically means that it's not linear, right? We're not adding or subtracting the same thing, the first order differences. But when it comes to the second order differences, then we see that constant change, okay? So a quadratic function can be defined by this equation, an equation of the form y, or if you're dealing with a function f of x, equals ax squared plus bx plus c, where a cannot equal 0. Because if a equals 0, you guys, then we're just dealing with a line, all right? So x here is our independent variable, our input. Y is the dependent variable, our output. And a, b, and c are constants, okay? They can be any constant, all right? It just means that they are a number, some constant number. So this is what a quadratic function looks like, and that should look sort of familiar to you. I'm sure you've seen functions of this form in your math travels before, okay? Ax squared plus bx plus c, that's a polynomial. And the thing about quadratic functions is that the highest degree in that polynomial is going to be degree 2. So ax squared plus bx plus c, we call a second order polynomial, which all that means is that the highest power in your polynomial is 2, okay? And listen to what I just said, you guys. I just said that it is called a second order polynomial. Second order differences, okay? That I want you to hopefully, help you remember this, okay? That this whole idea that the second order is really important, right? When we look at those tables of values, the second order differences, we want that to be constant, all right? That's important because it's this whole idea of this second order polynomial, which means that we have the highest degree of our polynomial is 2, right? We cannot have ax cubed, ax to the fourth, ax to the fifth. No, that's no longer a quadratic function. Our quadratic function, the highest degree that we are going to be dealing with is this degree 2, this second order polynomial, okay? So this whole idea of a second order is really important. So I am going to sort of jump ahead in this launch. I am jumping to Roman numeral number 5, where it says write an equation or formula to represent the function, because I think it's important to sort of have that worked out before we jump into the other parts of this question. So this launch, I should say. So I'm going a little bit out of order. Bear with me. So quadratic functions. What is our function? We're going to write it right now. Okay, you guys? So we just learned that a quadratic function can be defined by an equation of the form f of x equals ax squared plus bx plus c, where a cannot equal 0. And remember, we said that is because if a equals 0, you guys, then we're going to have 0 times x squared, which is just going to make this whole thing go away, and we're left with bx plus c, which is a line, all right? So a cannot equal 0 if this is a quadratic function. X is our input, y is our output, and a, b, and c are constants. That means that these coefficients here, this a and b and c here, they're just numbers, okay? And they can be any number. And of course, that depends on what our input and output are. What our function is, I should say. Okay, so let's see what function we are dealing with first. And you're going to see that in this unit, unit 4, you guys, when we're looking at quadratic functions, this unit's going to be a little different because I'm not really going to be asking you to write the quadratic function. You're going to be given it, okay? And we're going to sort of study it from there. In our last 2 units, right, you had to look at these tables of values and you had to figure out, okay, what's for lines, what's the slope and what's the y-intercept, and write the function yourself. And when we dealt with exponential functions, again, you had to look for what's the constant multiplier, what's the y-intercept, the initial value, and then you had to write that function, okay? In this unit on quadratic functions, we are going to be looking at tables of values, yes. But we're not going to be determining the function ourselves. We're basically going to be given the function and then we're sort of going to study how it behaves. Okay, so this is going to be a little bit different. So I'm going to give you this function. This function we would write as, using our variables, a of s equals s squared. Okay, so the area of our garden is going to equal the side length squared. And if we look at our table of values here, that should be very clear. So if the side length is 1 foot, then 1 squared is, of course, 1. If the side length is 2 feet, well, 2 squared is, of course, 4. And if the side length is 3 feet, well, then 3 squared is, of course, 9. If it's 4 feet, 4 squared is 16. And if it's 5 feet, 5 squared equals 25, right? So when we plug in our side length, we're simply squaring it to get our area, right? So this is our quadratic function for this particular table of values. And you're probably looking at this and saying, wait a second, you told me that the general form of a quadratic function is f of x equals ax squared plus bx plus c. What happened to these other things that should be at the end of this quadratic function? Where are they, right? Where's this bx plus c? Well, remember, you guys, a, b, and c are constants, all right? Which means that that constant could be 0. So in our particular function, a of s equals x squared, our constant a is 1, our constant b is 0, and our constant c is 0. So if we take that general form and put it in terms of our function, basically what we're saying is our function a of s equals 1s squared plus 0s plus 0. Okay, so if b equals 0, this just goes away. And if c equals 0, well, that just goes away. And so we're left with 1s squared, which is just s squared, right, you guys? So this is a quadratic function. It's just that our b and our c constants are 0, right? They're equal 0, so we don't see them, okay? So this is the quadratic function where a equals 1, b equals 0, and c equals 0. So here we have our quadratic function, a of s equals s squared, all right? So that's the function we're going to be dealing with for this launch. So now it's time for our favorite question. I'm sure you all knew it was coming. Roman numeral number 3, identify the real world domain and range, okay? And I wrote, hint, this is subjective. It will depend on the size of your yard. Guys, this is incredibly subjective. What do we say in this class all the time, right? This class is very different than other math classes because we are being asked to think about very specific real-world situations. There is not a one-size-fits-all answer for these questions, a lot of these questions, all right? It really is dependent on what you're working with. So guys, we are trying to figure out, right, how big can this garden be? And that really depends on the size of your yard. My yard might be very, very small in comparison to yours. So the size of my garden, the side length and the area of my garden will have to be a lot smaller than maybe the side length and area of a garden in your yard, because you might have a way bigger yard than me. So you really have to just stop and think about what you think is reasonable when you're thinking about the domain and range, right? So we know that our function here, a of s equals s squared, right? We're just squaring the side length to find our area, okay? And we need to stop and think about what would be a reasonable side length and area for our yard. And for me, it might be different than what it would be for you. So I want you to just take a moment to stop and think, all right, about how big your side length and area could be for your garden in your yard. There is not one correct answer for this. It's really very dependent, but you need to think about what would be reasonable, all right? So pause the video, take a moment, and stop and think about the size, what could be a reasonable side length and area for a garden in somebody's yard. So hopefully you've taken a minute to stop and think about this, okay? So I decided that my domain was going to go from 0 to 5 feet. I could accommodate a garden, where a square garden, where the length of each side was 5 feet long, right? So, you know, it can start at 0 feet. So basically I would have no garden and I could go up to 5 feet, all right? Which means that my range, okay, would go from 0 to 25 square feet. Remember, your domain is your input. So for us, that's our side length, right? And our range is our output, okay, our area. And how do we calculate the area, right? Well, we take our side length and we square it. So 0 squared gives me 0, and 5 squared gives me 25, okay, which is where this number came from. So the area of my garden is going to be anywhere between 0 and 25 square feet, which is where my range is coming in. Now for you, maybe you have a really, really, really big yard and you said, okay, well, my side length could go all the way up to 6 feet. Maybe you could accommodate a square garden where it's 6 feet by 6 feet. So then your range would look a little bit different. Your range would then go from 0 to 6 squared, which would be 36 square feet, okay? So it's all about what you think is reasonable here. Or maybe you have a really small yard and you said, I can only accommodate a 3 by 3 garden. So your domain would go from 0 to 3 feet, and then your range would go from 0 to 3 squared, which would be 9 square feet. So your range would be 0 to 9 square feet, all right? It's really very subjective. It depends on what you think is reasonable, okay? So now we move down to Roman numeral number 4, where it says create a graph for the function. So we're going to take our table of values, the table of values we've been working with from the beginning, and we're just going to plug in those ordered pairs, right? Our input-output pairs. So 1, 1, and 2, 4, and 3, 9, and 4, 16, and 5, 25. And we're going to see what's happening with this graph. What does it look like? What is it shaped like, right? We saw that obviously a linear function looked like a line. We saw that an exponential function had this shape where it was either increasing or decreasing, but really, really quickly. And then we had that asymptote at the x-axis. So like, what's going to happen with our quadratic functions? Let's take a look at the graph, because as we saw in our last 2 units, the graph's really important. It tells us a lot of really important information. It gives us a lot of really good visual information. So let's take those ordered pairs, plug them in, and graph them. Right? And when we do that, this is what we get, okay? Now, this is what I'm going to call the graph of our real world domain. So this is the graph that we looked at for our particular situation, okay? So here was our quadratic function, right? A of s equals s squared. This is the graph of a of s equals s squared from basically what we defined as our domain, from 0 to 5. And you can see those ordered pairs that we talked about in the table, right? Here's 1, 1 right here. Okay, and then of course we have 2, 4 right here. And then we have 3, 9 right there. And 4, 16 is right here. And then 5, 25 is right up here, okay? And there's the line that we saw that we can sort of make through there. And of course, 0, 0 is part of our domain. We did say we were going from 0 to 5 feet, so I don't want to forget that. 0 squared is 0. Okay, so this is our real world domain. This is what the graph of our real world domain. This is what the graph looks like. The part of the graph looks like for this particular piece of our quadratic function. So where our domain went from 0 to 5. Okay, our inputs and outputs for our domain and our range for the inputs 0 to 5. Okay, this is what the graph looks like. But this just gives us a piece of what a quadratic function looks like. I also want to show you the mathematical graph of this. So basically the mathematical domain from where we consider every input. So if we considered every input, right, what would that graph look like? Now, it makes sense that our real world domain does not have any negative numbers, right? We didn't look over here on this side of the x-axis. Like if I had extended this, right, then it would go -1, -2, -3. We didn't see any negative inputs because, you guys, we were thinking about lengths of a garden. You're not going to have a garden with a length of -1 feet. It doesn't even make sense. We wouldn't even consider that for our function that our real world, for our domain of the function that we're working with, okay? Our real world domain does not consider negative numbers at all. It doesn't make sense for our situation, right? You're not going to have a garden with a negative length of a side. That doesn't make any sense. Okay, so we didn't even consider negative inputs, okay? But if we want to see and really think about a quadratic function as a whole, I do want to show you what it looks like when we look at what I'm going to call the mathematical domain of this function. So we're going to look at a of s equals s squared for all inputs, okay? And this is what it looks like, all right? We get this lovely U-shaped graph, okay? So this is going to represent what I'm calling mathematical domain, okay? The entire graph of a of s equals s squared, where we consider all inputs. And this U shape that we see has a name. It's called a parabola. So graphs of quadratic functions, okay, have this shape that we call a parabola. And it's this U shape here, okay? And it can be it can be shaped like this, a U. It could also be flipped and shaped like an A, okay? But you're going to start to see this what we call parabolic shape, okay, for a quadratic function, all right? That's important to know. And we can see, so we talked a lot about x-intercepts too when we were talking about linear and exponential functions, right? Our linear function could have one x-intercept, right, where our graph hits the x-axis. Our exponential function could have had, didn't have any because that x-axis was an asymptote, so it never touched it. Well, our parabola can have, as it turns out, no x-intercept, one x-intercept, or even two x-intercepts, okay, which is pretty cool. So quadratic functions, our x-intercepts are going to behave a little bit differently as well. So, but really what I want you to know is that when we are working with quadratic functions, we get this U shape and it's called a parabola. And this is actually a very special shape, and we'll talk about that a little bit more on the next slide. So I just want you guys to just sit back and listen to this part, okay? Parabolas are very special. Quadratic functions are very useful in the real world, all right? You know, people always ask, when am I going to use this? When am I going to use this? When am I going to use this? So I really think it's important to talk about when we're studying these new concepts, these new functions, like when are you going to use them in the real world? And parabolas have a lot of really important real world functions. So let's talk about these real world applications of quadratic functions. So parabolas are a very useful conic section, okay? They have what's something called a focal point. And because of this, we can use parabolas for telescopes, satellite dishes, flashlights, car headlights, trough solar collectors. These are all parabolic, okay? So let's look at some examples. There's a satellite, and you can see inside that shape, there's a parabola going on all throughout that, okay? This is a flashlight, you guys, all right? You see the parabola in there, okay? So very, very useful. We also see parabolic arches in architecture, like arches and bridges and things like that. For example, the Golden Gate Bridge is designed using parabolic cables, okay? It's really cool. We also use quadratic functions to model projectile motion, so throwing or launching objects, and to describe revenue, profit, and cost functions in business, okay? So look at this, right? When you throw a ball, and in this picture it's a basketball, it goes up, 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 but then of course it starts to come down. And what does that look like, you guys? That looks like a parabola, right? So we can actually model these motion and describe motion, projectile motion, using a quadratic function. And we can also model revenue, profit, and cost in businesses using quadratic functions. So they are incredibly useful functions, you guys. They are worth our time. They are worth our study, okay? So I just wanted you to see just some really cool real-world applications of these functions that we're studying, because they're awesome. So now let's sum up the most important pieces of information that we learned about quadratic functions today, okay? Beginning with how we define it. So a quadratic function can be defined by an equation of the form f of x equals ax squared plus bx plus c, where a cannot equal 0, remember, because then we're dealing with a line, right? Then this becomes 0, and we're just left with bx plus c, which is the equation of the line, all right? X is our independent variable, our input, y or f of x is our dependent variable, our output, and a, b, and c are constants, okay? They are just numbers, all right? We also talked about how quadratic functions are described using second-order polynomials, right? This right here is a second-order polynomial, which just means that our exponent here is 2, okay? Second order. Our exponent is 2. The highest power is 2, okay? And that was important because we learned that quadratic function tables are tables of values characterized by constant second-order differences. So this whole idea of a second order is really important when it comes to quadratic functions, right? So quadratic function tables are tables of values characterized by constant second-order differences of the output when the input increases by a constant, okay? So we took it one step further. We didn't just look at the change from one output to the next, the first order change. We then looked at those differences and saw that there was a pattern with those second order differences, okay? So we looked at our first order differences and said, oh my gosh, there's a pattern there, all right? And we calculated our second order differences and found that to be a constant, which meant we were dealing with a quadratic function. We also learned that graphs of quadratics are called parabolas, those special U-shapes that look like this, all right? And we learned that parabolas are very useful in the real world, okay? We see them in architecture. They can be used to describe motion. They can be used to describe business models, and they are found all over the place where in real world applications where we need to use that focal point. So we see them in satellites and flashlights and in all different places. So I hope you enjoyed your little introduction to quadratic functions. They are incredibly useful, incredibly important, and we are going to have a great time sort of analyzing them and seeing how we can use them in the real world.